Chapter 9, Audit Sampling. Audit sampling, whether statistical or non-statistical, is the process of selecting and evaluating a sample of items from a population of audit relevance such that the auditors expect the sample to be representative of some characteristic, qualitative or quantitative, of the population. In this context, representative means that the sample will result in conclusions that are similar to those that would be drawn if the same procedures were applied to the entire population. Basic to audit sampling is sampling risk, which is the risk that the auditor's conclusion based on a sample might be different from the conclusion they would make if they examined every item in the entire population. Sampling risk is reduced by increasing the size of the sample, but auditing large samples or the entire population is costly. Non-sampling risk is the risk that auditors may fail to apply appropriate audit procedures, or they may fail to recognize errors in the documents or transactions that are examined. Non-sampling risk can generally be reduced to low levels through effective planning and supervision of audit engagements and implementation of appropriately designed quality control procedures by the CPA firms. Statistical sampling involves the use of an appropriate statistical technique to evaluate sample results. Alternatively, a sample is said to be non-statistical when the auditors use judgment rather than statistical techniques to measure sampling risk. This is not to say that non-statistical samples are carelessly selected samples. Indeed, both non-statistical and statistical audit samples should be selected in a way that they may be expected to allow the auditor to draw valid inferences about the population. However, non-statistical sampling provides no means of quantifying sampling risk. Thus, auditors may find themselves taking larger and more costly samples than are necessary or unknowingly accepting a higher than acceptable degree of sampling risk. Through statistical sampling techniques, the auditors may specify in advance the sampling risk that they want in their sample results and then compute sample size that controls sampling risk at the desired level. Since statistical samples are based on the laws of probability, the auditors are able to control the extent of sampling risk in relying upon sample results. Advantages of statistical sampling include designing efficient samples, measuring the sufficiency of the evidence obtained, and objectively evaluating sample results. However, these advantages are not obtained without additional cost of training the audit staff, designing sampling plans, and selecting items for examination. For these reasons, non-statistical samples are widely used by auditors, especially for tests of relatively small populations. A common mistake is to equate statistical sampling with random sampling. Random sampling is simply a method of selecting items for inclusion in a sample. It can be used with either statistical or non-statistical sampling. The principle involved in unrestricted random selection is that every item in the population has an equal chance of being selected for inclusion in the sample. Although random selection results in a statistically unbiased sample, it is not necessarily a representative sample. Sampling risk still exists purely by chance. A risk still exists that a sample will be selected that does not possess essentially the same characteristics as the population. However, this risk can be measured by statistical formulas. Random sampling techniques include random number tables, random number generators, and systematic selection. This slide shows a table of random numbers. This is one of the easiest methods of selecting items at random. In using a random number table, the first step is to establish correspondence between the digits in the table and the items in the population. This is most easily done when the items in the population are consecutively numbered. When using a random number table, the auditor will need to determine if they are sampling without replacement or with replacement. If they draw the same number twice and ignore the number the second time, This is sampling without replacement. If they allow an item to be selected twice, they are sampling with replacement. Most auditors will use sampling without replacement, which results in a slightly smaller sample size. Other methods of selecting the sample include haphazard selection, where the auditors select the items from the population on an arbitrary basis, but without any conscious bias. Block selection, which involves a block sample of all items in a selected time period. Numerical sequence or alphabetical sequence. Neither haphazard or block sampling can be used with statistical sampling plans because they are not based on probabilistic methods. The last technique is stratification. This technique divides the population into relatively homogeneous subgroups called strata. These strata then may be sampled separately, and the sample results may be evaluated separately or combined to provide an estimate of the characteristics of the total population. The effect of stratification is to require a smaller number of sample items to evaluate. Stratification allows the auditors to apply different audit procedures to each stratum. This slide shows an example of stratification of accounts receivable balances. The large accounts over $10,000 will all be examined, and 50 accounts from the next group from $9,999.99 to $5,000 and 30 from the less than $5,000 group. When auditors are sampling, they generally will not accept sampling risk for any item that by itself could materially misstate the population. So they will test every item that is more than the tolerable misstatement and sample from each of the additional strata. The sampling procedures used to accomplish specific audit objectives are called sampling plans. Statistical sampling plans may be used to estimate many characteristics of a population. The major types of sampling plans used for audit sampling include attribute sampling, which enables the auditors to estimate the rate of occurrence of certain characteristics in the population and is frequently used in performing tests of controls. Discovery sampling is a form of attribute sampling that is designed to locate at least one deviation in the population and is used when the auditors expect a very low rate of occurrence of some critical deviation. Classical variable sampling are the applications that provide the auditors with an estimate of a numerical quantity, such as the dollar balance of an account. Types of classical variable sampling include mean per unit estimation, ratio estimation, and difference estimation. Monetary unit sampling applies attribute sampling theory to estimate the dollar amount of misstatement in a population. This is used as an alternative to classical variable sampling methods. Sometimes one sampling plan may be used for the dual purpose of testing a control and substantiating the dollar amount of an account balance. For example, a dual purpose test might be used to evaluate the effectiveness of a control over recording sales transactions and to estimate the total overstatement or understatement of the sales account. The allowance for sampling risk is the amount used to create a range set by plus or minus limits from the sample results from which the true value of the population characteristic being measured is likely to lie. The allowance for sampling risk is also called the precision. The wider the interval that we allow, the more confident we may be that the true population characteristic is within it. While being more confident that the true population characteristic falls within an interval is desirable, we realize that the increased size of the interval leads to a less precise conclusion. The allowance for sampling risk may also be used to construct a dollar interval. The size of the sample has a significant effect on both the allowance for sampling risk and sampling risk. With a very small population, we cannot have low sampling risk unless we allow a very large allowance for sampling risk or precision. As the sample size increases, both sampling risk and the allowance for sampling risk decrease. In other words, the smaller the allowance for sampling risk, or the smaller the sampling risk desired by the auditors, the larger the required sample. Sample size is also affected by certain characteristics of the population being tested. As the population increases in size, the sample size necessary to estimate the population with specified sampling risk and allowance for sampling risk will increase. However, if the population size is above approximately 500, an increase in its size has only a very small effect on the required sample size. When performing tests of controls, the auditors are concerned with two aspects of sampling risk: the risk of assessing control risk too high and the risk of assessing control risk too low. The risk of assessing control risk too high relates to audit efficiency and is the possibility that the sample results will cause the auditors to assess control risk at a higher level than is warranted based on the actual operating effectiveness of the control. The risk of assessing control risk too low is the more important because it relates to audit effectiveness and is the possibility that the sample results will cause the auditors to assess control risk at a lower level than is warranted based on the actual operating effectiveness of the control. Efficiency means more work is performed than is necessary, but effectiveness means that the auditors may miss detecting material misstatements in the client's financial statements. Attribute sampling for test of controls generally involve these steps. First, the auditor determines the objective of the test, defines the attributes and deviation conditions, and the population to be sampled. Next, the risk of assessing control risk too low and the tolerable deviation are specified. The auditor then estimates the expected population deviation rate and determines the sample size. The sample is selected, tested, and the results are evaluated. Last, the auditor documents the sampling procedure. The AICP Audit Guide states that audit sampling includes this chart of overlapping ranges to illustrate the planned assessed level of control risk and the tolerable deviation rate. Auditors specify the tolerable deviation rate based on their planned assessed level of control risk and the degree of assurance desired from the audit evidence in the sample. The lower the planned assessed level of control risk, or the more assurance desired from the sample, the lower the tolerable deviation rate. Three major factors determine the sample size for a test of controls: the risk of assessing control risk too low, the tolerable deviation rate, and the expected population deviation rate. In this example, the auditor has decided on a risk of assessing control risk too low of 5% and a tolerable deviation rate of 7% and an expected population deviation rate of 1.5%. In the next slide, we will see how to determine the sample size and allowable deviations in the sample. To enable auditors to use attribute sampling without resorting to complex mathematical formulas, tables have been developed such as the one in this slide. This table is for statistical sample sizes for tests of controls at 5% risk of assessing control risk too low. The auditor would then find the expected population deviation rate of 1.5% in the left column and the tolerable deviation rate of 7% across the top, and where the horizontal and vertical columns intersect at 66 with 1 in parentheses would show the sample size of 66 with no more than 1 deviation in the sample. The tables presented in this chapter may be used to evaluate sample results in two different but related ways. The first approach is to use Table 9.4 that we used in the previous slide. When the number of deviations found in the sample does not exceed the allowable number of deviations, which in this example was 1, the auditors conclude that the population deviation rate does not exceed the tolerable deviation rate. On the other hand, when the number of deviations in the sample exceeds the allowable number of deviations, the auditors conclude that the population's deviation rate exceeds the tolerable deviation, and therefore they generally increase their assessed level of control risk. We will illustrate the second approach in a future slide. Continuing with this example, we have tested the sample and found there were no deviations in the sample. Using the first approach, we can see that the sample achieved the planned level of control risk at 5% because there was one deviation allowed in the sample and none were found. We can now say that we believe that the population deviation is less than 7% with a 5% risk of assessing control risk too low. However, using the second approach with table 9.5 at a sample size of 65, the closest to our actual sample of 66, and 0 errors, we can find the upper deviation rate is 4.6. We have achieved the planned level of control risk, but now we can say that we believe that the population deviation is less than 4.6, with a 5% risk of assessing control risk too low, a more precise conclusion. Continuing with this example, but now you find that there are 3 deviations in the sample. Using the first approach, you will find that the planned level of control risk was not achieved because only 1 deviation was allowed and 3 were found. Substantive testing will have to be increased in the area of this control. A second approach is to use this table 9.5 to obtain a more precise conclusion, one which includes determining the achieved upper deviation rate. Using this approach, we determine that the achieved upper deviation rate is 11.5%. Since this is greater than the tolerable deviation rate of 7%, we conclude that the sample does not meet the auditor's objective and therefore more substantive testing is appropriate. Other statistical attribute sampling approaches include discovery sampling, which is actually a modified case of attribute sampling. The purpose of a discovery sample is to detect at least 1 deviation with a predetermined risk of assessing control risk too low if the deviation rate in the population is greater than the specified tolerable deviation rate. One important use of discovery sampling is to locate examples of a suspected fraud. Another approach used in practice is sequential or stop and go sampling. Under a sequential sampling plan, the audit sample is taken in several stages. The auditors start by examining a small sample. Then, based on the results of this initial sample, they decide whether to assess control risk at the planned level, assess control risk at a higher level than planned, or examine additional sample items to get more information. The audit sampling steps for substantive tests involve determining the objective of the test, defining the population and sampling unit, and choosing an audit sampling technique. Then the auditor determines the sample size, selects test, and evaluates the sample results. Last, the auditor should document the sampling procedure. Similar to sampling risk for test of controls, there are 2 aspects of sampling risk for substantive procedures. The risk of incorrect rejection, alpha risk, of an account. This is a possibility that sample results will indicate that an account balance is materially misstated when in fact it is not misstated, or the risk of incorrect acceptance, beta risk, of an account. This is a possibility that sample results will indicate that an account balance is not materially misstated when in fact it is materially misstated. The nature of these risks parallels the sampling risk of test of controls. If the auditors make the first type of error and incorrectly reject an account balance, their audit will lack efficiency since they will perform additional audit procedures that will eventually reveal that the account is not materially misstated. If the auditors make the second type of error, incorrect acceptance, the effectiveness of the audit is compromised. Therefore, the risk of incorrect acceptance is of primary concern to auditors. This slide illustrates the factors that affect sample size for substantive procedures. First, the auditor's requirements affect the sample size. If the auditor increased the risk of incorrect rejection, acceptance, or tolerable misstatement, then the sample size decreases. Next, the population characteristics affect the sample size. If there are increases in the population size, standard deviation, or expected misstatement, then the sample size will also increase. Next, we will review modules B and C that cover classical variable sampling and non-statistical sampling methods. In Module B, we will cover 3 methods of classical variable sampling: Classical variable sampling plans enable auditors to estimate a numerical quantity such as the dollar amount of an account balance. This makes these techniques particularly useful for performing substantive procedures. Classical variable sampling methods include mean per unit, ratio estimation, and difference estimation. Mean per unit estimation enables auditors to estimate the mean audited value of the items in a population with specified sampling risk and allowance for sampling risk or precision by determining the mean audited value of the items in a sample. An estimate of the total audited value of the population is obtained by multiplying the sample mean, the average audited value of the sample, times the number of items in the population. The projected misstatement that may then be calculated as the difference between the estimated total audited value and the client's book value. The assumption underlying mean per unit estimation is that the sample's mean audited value will, for certain sampling risk and allowance for sampling risk, represent the true audited mean of the population. This slide illustrates a problem using mean per unit estimation. In this example, the population size is 100,000 sales invoices with a book value of $6,250,000. The auditor has set the tolerable misstatement at $364,000 and the sampling risk of incorrect acceptance at 5% and incorrect rejection at 4.6%. This table shows the risk coefficients of incorrect acceptance and incorrect rejection at different levels of acceptable risk. In our example, the incorrect acceptance coefficient would be 1.64 and the incorrect rejection coefficient would be 2.00. We determine the sample size, 225, by multiplying the number of sales invoices, 100,000, by the sum of the incorrect acceptance and rejection coefficients, 1.6 and 2.00, and the estimated standard deviation of $15, and divide this by the tolerable misstatement of 364,000. After selecting the sample of 225 accounts, we would perform the audit procedure. The results of the sample would be calculated and the mean or average of the sample values would be calculated. If we found a mean of $61 for the sample and we have a population of 100,000 accounts, then we could estimate the total value of the population as $6,100,000. Subtracting this amount from the book value of the population, $6,250,000, gives a projected misstatement of $150,000 overstatement. Next, we would determine the acceptable interval by calculating the adjusted allowance for sampling risk of $189,067, and the confidence interval would be $5,910,933 to $6,289,067. The confidence interval is calculated by taking the adjusted allowance for sampling risk of $189,067 and subtracting it from the point estimate of $6,100,000 and adding it to the point estimate. Because the confidence interval does contain the book value of $6,250,000, we would accept the book value as materially correct. The auditor should also consider qualitative aspects of any misstatement found in their sample. Mean per unit estimation uses the mean audited value of the sample as the basis for estimating the projected misstatement and total audit value of a population. Two other options are difference and ratio estimation. In applying difference estimation, the auditor uses a sample to estimate the average difference between the audited value and book value of items in a population. The average difference is estimated by dividing the net misstatement in the sample by the number of items in the sample. The projected misstatement is determined by multiplying the estimated average difference by the number of items in the population. The formula is shown above. Difference estimation is most appropriate when the size of misstatements does not vary significantly in comparison to book value. In ratio estimation, the auditors use a sample to estimate the ratio of the misstatement in a sample to its book value and then project it to the entire population. The ratio of misstatements is simply the sample net misstatement divided by the book value of the items in the sample. An estimate of the projected misstatement is obtained by multiplying this estimated ratio by the total book value as shown in the formula in this slide. Ratio estimation is preferred when the size of misstatement is nearly proportional to the book values of the items. In other words, it is appropriate when larger accounts have large misstatements and smaller accounts have small misstatements. The major differences between statistical and non-statistical sampling in substantive testing are in the procedures used to determine the sample size and evaluate the sample results. In using non-statistical sampling, the auditors may decide not to quantify the factors used to arrive at the sample size. In evaluating sample results, the auditors also project the misstatements found in the sample to the population and consider sampling risk, but the level of risk is not quantified. Many CPA firms have adopted structured approaches to non-statistical sampling that are based on statistical methods. This increases the consistency of sampling judgments that are made by various auditors throughout the firm. In this slide, we have information to use in a non-statistical variable sampling problem. The population is 2,000 items with a book value of $3 million and a tolerable misstatement of 100,000. The risk assessment is that inherent and control risk is slightly below maximum and other substantive test is moderate. Non-statistical sampling will use a reliability factor selected from a table such as the one that is illustrated in this slide. This reliability factor is based on the auditor's combined assessment of inherent and control risk and the auditor's assessment of the risk that other substantive procedures will fail to detect a potential misstatement. For this example, we will choose a reliability factor of 2.0 based on a combined assessment of inherent and control risk slightly below the maximum and a moderate risk that other substantive procedures will fail to detect a material misstatement. We then multiply the reliability factor by the population's book value and divide by the tolerable misstatement to determine the sample size of 60 items. After the sample items are audited, it is determined that there was a $6,600 net misstatement for the sample, which has a book value of $1,100,000. We divide the misstatement by the book value and multiply by the book value of the population to determine the projected misstatement of the population of 18,000. We then compare this to the tolerable misstatement of 100,000 and conclude the account balance is not likely to be misstated since the projected misstatement is only 18% of the tolerable misstatement. And this is the conclusion of the presentation for Chapter 9.